This lecture is about functional groups and organic nomenclature. You will learn what functional groups are, why they're important, and how to name functional groups in organic compounds. What is a functional group? A functional group is a covalently bonded collection of atoms that has specific reactivity or function. And here are some examples. The carboxylic acids have the structure CO2H, that is C double bonded to O and C single bonded to OH. Carboxylic acids all have a sour taste. That would be a function that you would experience if carboxylic acids were to touch your tongue. They also undergo a reaction with the base sodium hydroxide. RCO2H plus NaOH produces the salt RCO2 minus Na+, which is a sodium carboxylate, plus water. Vinegar is an example of a carboxylic acid solution. It contains 5% acetic acid, or R equals CH3, dissolved in water. Alcohols have an OH group connected to an sp3 hybridized carbon. These are very weak acids, so they don't react with sodium hydroxide. However, they do react with sodium metal. And when that happens, the sodium metal will react to form a sodium alkoxide, hydrogen gas, and a lot of heat. In fact, there's usually enough heat, if this is done in the presence of air, to make the hydrogen react with oxygen and explode into flame. Alkenes, which have the structure C double bond C, perform addition reactions. That is, the pi bond, which is the weakest bond in the C double bond C structure, will break, reacting with another molecule to form two new sigma bonds. So, for example, you see there's an alkene reacting with hydrogen gas in the presence of platinum, which is a catalyst, and that forms an alkane where there is no longer a carbon-carbon pi bond, just carbon-carbon single bonds, and each carbon received a hydrogen atom. So a hydrogen atom added to each carbon that was in the carbon-carbon double bond. Amines have an sp3 hybridized nitrogen connected to at least one carbon, but not C double bond O. When nitrogen is connected to C double bond O, that's called an amide. Now amines, they smell fishy, very obvious. They also have a bitter taste. And if an amine reacts with a carboxylic acid, you get a salt. Now the difference between this salt and the original amine is that although the amine smelled fishy, the salt has almost no smell. So reacting amines, such as found in fish, with something that contains a carboxylic acid, such as the citric acid in lemon juice, will eliminate the smell. So it's quite useful application of the reactivity of amines and that of carboxylic acids in cooking. Thiols have the structure SH. Thiols are incredibly smelly. And one way to get rid of that smell is to take the thiol and react it with sodium hydroxide, similar to carboxylic acids, and you will form Rs minus Na+, which is a thiolate salt. This has very little or no smell, and you will also form water. Which functional group is a base? By that we mean a proton acceptor. Amines are the only practical bases towards dilute strong acids like HCl and carboxylic acids, which we saw in the previous slide. Any functional groups with a lone pair could react with very strong acids like concentrated sulfuric acid, H2SO4. These are very atypical conditions. So other functional groups, amides, etc., are considered not basic. When you are learning the functional groups, you need to do the following. Memorize the names and structures of the functional groups in Table 3.1 in Chapter 3. Practice identifying functional groups in the exercises. Click the link to Table 3.1 in Chapter 3 to work on the following practice problem. Practice Problem 1. Identify the functional groups, except for alkanes, in the following compounds. You have two medicinally significant compounds here, bupivacaine, which is a local anesthetic used as a nerve block in surgery, and meropenem, which is a very broad-spectrum injectable antibiotic, highly useful against drug-resistant bacteria. Now at this point, you want to pause the video so you can work on the problem. Answers to practice problem 1. For bupivacaine, we have a benzene ring, an amide, and an amine. For meropenem, we have an alcohol, an amide, a carboxylic acid, an alkene, a thioether, an amine, and an amide. Note that the functional groups shown below can be pronounced amide, amide, or amide, depending on your mood. Practice problem 2. The anesthetic bupivacaine is given to patients intravenously, that is, injection into a vein, or epidural, which is injection into the outermost portion of the spinal canal. Since bupivacaine does not dissolve in the water in your body, the drug is converted into a salt with HCl, bupivacaine hydrochloride, then made into a sterile 0.5% weight over volume aqueous solution for use. Draw the reaction of bupivacaine and HCl and the structure of bupivacaine hydrochloride and justify where you place the proton from HCl. Now you may pause the video to work on this problem. Answers to practice problem 2. As you can see in the reaction, only one of the nitrogens is capable of picking up a proton from HCl, and that's the nitrogen from the amine. Amines are the only real bases among the functional groups that you've learned. The amide nitrogen is not basic and therefore does not react with HCl. So in the final product, you show a bond between the amine nitrogen and the proton, and you form a salt. Organic nomenclature, or naming organic compounds, requires several skills. Knowing how to find and name the largest contiguous, which means no breaks, no oxygens or nitrogen atoms in between, carbon chain, or ring, is the first skill that you have to have. The example shown, the longest carbon chain is 9 carbons long. Now that can either be numbered from left to right or from right to left. Next, you need to know which direction to number the chain. So how to number and name the substituents or groups attached to the largest carbon chain is another skill that you have to have. From that previous example, the numbering should be from left to right because you want to give the lowest possible numbers to the substituents that are attached to the longest contiguous carbon chain. These substituents would be named methyl and propyl, and specifically, based on their numbers, they would be 3-methyl, 6-propyl. Note that we're using the lowest numbers for these substituents or groups, and we're placing them in alphabetical order. Another thing you have to know about organic nomenclature is how to end the name with the dominant functional groups that determine the suffix, that is the ending, of the name. If there are no carbon-carbon double bonds or carbon-carbon triple bonds in the longest carbon chain, then the suffix or ending will be ane, A-N-E. For example, we just saw in our previous example that when the longest carbon chain is 9 carbons and we have a methyl and a propyl at positions 3 and 6, we would number those positions 3-methyl and 6-propyl and put them in that alphabetical ordering, M before P. Since there are 9 carbons, the prefix for 9 carbons is known, and the suffix, since there is no carbon-carbon double bond or triple bond, is ane. And so its complete name would be 3-methyl 6-propyl nonane. If there is a carbon-carbon double bond in the longest carbon chain, then we number the position of the first carbon in that carbon-carbon double bond, and we end the name with the ene suffix, E-N-E. So for example, if you number that molecule shown from right to left to give the carbon-carbon double bond the lowest possible number, then chlorine is to position 5, the carbon-carbon double bond starts at position 1, and the name will be 5-chloro for the position of the chlorine substituent, pent for the number of carbons, 1-ene. If there is a carbon-carbon triple bond in the longest carbon chain, then we use a numerical designation for the position of the C triple bond C, followed by YNE or ine. Again, we want to use the lowest possible number for C triple bond C. So in the example shown, we number from right to left, and C triple bond C will start at position 2. We also have 2 methyl groups at position 4. Since we have 2 identical groups, we have to use the prefix di. So the full name will be 4,4-dimethyl, hept, since there are 7 carbons, 2-ine. Now let's just go over the duplication prefix again. Di is 2 identical groups, tri is 3, tetra is 4, etc. Answers to practice problem 3. In part A, the longest carbon chain has 10 carbons, and at position 2 there's a chloro group. At position 6 there are 2 ethyl groups. So the name for this compound would be 2-chloro 6,6-diethyl decane. In part B, the longest carbon chain containing C double bond C has 7 carbons. C double bond C begins at carbon 1, and there's a nitro group at position 2. So the name for this compound is 2-nitro hept 1-ene. In part C, the longest carbon chain containing C triple bond C has 6 carbons. C triple bond C begins at position 3, and there's an azeto group at position 2. Note we count from right to left because we're going to get position 3 to be the numbering for C triple bond C in either direction, but we can give a lower number for the substituent, the azeto group, if we count from right to left. So we do that. That gives us the name 2-azeto hex 3-ine. In part D, the longest carbon chain has 8 carbons, and there is an isopropyl substituent at position 5 and a tert-butyl substituent at position 4. Now, an interesting thing to note about tert-butyl, since tert has a hyphen in front of butyl, it's made invisible to alphabetical ordering. So we really only consider the B in butyl in terms of alphabetical ordering, not the tert. So the name for this compound would be 4-tert-butyl, so B comes before I, 5-isopropyl octane. So far we've learned that naming organic compounds requires knowing how to find and name the largest contiguous carbon chain, but really haven't looked at a ring. Here's an example. We have a 4-sided ring. It has 2 bromines in one position and a butyl group in another position. So you need to know how to number that, and it turns out you want to number them with the lowest possible numbers. So the 2 bromines are at position 1 and the butyl is position 2. Now let's see why we need to number it that particular way. So we need to look at numbering and naming substituents or groups attached to the largest ring. The 2 bromines are at position 1 because it's dibromo. We ignore di in the alphabetical ordering. Br comes before Bu in butyl. Thus, we give position 1 to the dibromo and position 2 to the butyl. We always want the lowest total numbers on the ring. Thus, the final name would be 1,1-dibromo, numbers for the bromines, 2-butyl, then cyclo, which is the prefix for the ring, finally butane. 1,1-dibromo, 2-butyl, cyclobutane. If necessary, you may need to know how to name specific 3D arrangements of atoms in a molecule. One arrangement involves the cis orientation of groups, and we use the cis prefix for two identical groups pointing in the same general direction, that is, both up or down, attached to different atoms in a double bond or ring. So as you see in the examples, with a double bond, you can have two hydrogens, one coming off of each carbon in the double bond, pointing down, and that makes this cis, and the full name would be cis-hextuene. In the ring example, you have hydrogens at positions 1 and 3 pointing up, and there are other substituents at positions 1 and 3 as well, a chlorine and a fluorine. So the full name for this is cis-1-chloro 3-fluoro-cyclohexane. You can refer to the non-identical groups, for example the chlorine and the fluorine in the ring, as cis also. But the cis identifier only works if two identical groups, in these cases the hydrogens, are present on different atoms in the double bond or ring. When they aren't identical groups, let's say one of the hydrogens was a carbon atom, that would give us 4 different groups, and the cis prefix no longer works because we don't know what's on the same side. Much later in OChem 1 Intensive, we'll learn how to deal with 4 different groups. The trans prefix refers to two identical groups pointing in opposite general directions, that is, one is up and the other is down, attached to different atoms in a double bond or ring. So in our examples, we have 2 hydrogens, one on each carbon of the double bond, one pointing down, one pointing up, and that gives it a trans orientation. The name is thus trans-hextuene. In the ring example, the hydrogens are at position 1 and 3, one pointing down, the other pointing up, and the corresponding chlorine and fluorine atoms are pointing in opposite directions as well. This gives the molecule the name trans-1-chloro 3-fluoro-cyclohexane. As we learned with the cis example, you can refer to the non-identical groups, as in the case of the ring, chlorine and fluorine, as trans also. But, as before, the trans identifier only works if two identical groups are present on different atoms in the double bond or ring. Practice problem 4. Name each of the following compounds. Now, in this practice problem, you're going to be using cis or trans prefixes for some of the examples. And remember that when there's a double bond inside a ring, that you will assume that it's going to be cis, so you don't have to actually use the cis prefix. A trans double bond inside a ring would be unusual, and you'd actually have to put trans in the front of the name. Now you may pause the video to work on this problem. Answers to practice problem 4. In part A, we have a 7-sided ring, and we have to number the double bond with the lowest possible number, so we start with carbon 1 as the first carbon in the double bond. Then that makes carbon 2 the second carbon in the double bond, and chlorine is at position 3. So we say 3-chloro-cycloheptene. Note, there is no number needed for the carbon-carbon double bond because there is only one C double bond C. And as I mentioned, we assume that it is cis for the carbon-carbon double bond in the ring, and thus there is no cis prefix. In part B, we have bromines at positions 2 and 3, and the double bond is at position 2. Those two identical groups, the bromines, are pointing in opposite directions. The bromine at position 3 is pointing up, and the one at position 2 is pointing down. Thus, the prefix trans must be used, and the name is trans 2,3-dibromo hextuene. In part C, we have a ring again, and now the identical groups at positions 1 and 2 are hydrogens, both pointing up. The corresponding groups at those positions, a methyl group and a propyl group, are pointing down. We have cis orientation of the hydrogens, and of course the same for the corresponding groups at those positions. And our name would be cis 1-methyl 2-propyl cyclopentane. For alcohols, which contain the OH group, we use the lowest possible number for the carbon attached to OH. In fact, the position of the carbon with OH beats the C double bond C and C triple bond C priorities, meaning we always give the lowest number for the carbon attached to OH even if C double bond C or C triple bond C is present in the structure. In the case of a carbon chain without a carbon-carbon double bond, the ending of the alcohol would be "an", followed by the number for the position of the carbon with the OH, ending with the OL or all suffix. So in the example shown, we have 4 carbons. Numbering from right to left would give the lowest possible number for the carbon with the OH, and that would be 2. So that gives us the name butan-2-ol. In the case of a carbon-carbon double bond, you want the number for the position of the first carbon in C double bond C, followed by En, N, and the number for the position of the OH group with the ending "ol". So in our example, again we number from right to left because we want the OH to have a lower number than that for C double bond C, if that's possible, and it is in this case. And our name would thus be 3-butan-2-ol. In the case of a triple bond and an OH, we'd have the number for the position of the first carbon in C triple bond C, followed by Yn, and then the number for the position of the OH group, ol. So in our example, again counting from right to left, we have the name 3-butyne-2-ol. Practice problem 5. Name each of the following compounds. Now be sure that you note that there are going to be OH groups as well as carbon-carbon double or triple bonds present. Remember that the carbon with the OH group gets the lowest possible number. Answers to practice problem 5. In part A, we have a 7-carbon chain. The lowest number position should be 1 where the OH is. That puts the carbon-carbon double bond in position 3 and a methyl at position 5. Note also that the three-dimensional orientation of groups at positions 3 and 4 place hydrogens in opposite directions. Those are the atoms you don't see. And that makes this trans. So we have trans in the front, 5-methyl hept for 7 carbons, 3N, 3 for the position of the carbon-carbon double bond, 1-ol. Trans 5-methyl hept 3N 1-ol. In part B, we have a ring. It's got 6 carbons. Position 1 again would be for the alcohol. Position 3 is for the carbon-carbon double bond. So prefix here is cyclo for the ring. Cyclohex 3N 1-ol. In part C, we have an alkyne and an alcohol. Lowest possible number for the alcohol would be position 2, and the number for the carbon-carbon triple bond would be position 3. There's another ring attached to this chain. It's a small ring, a cyclopropyl group, and that's at position 4. So the name for this compound would be 4-cyclopropyl, 2-methyl, there's a methyl group at position 2, bute for the length of the carbon chain, 3-ine, 2-ol. 4-cyclopropyl, 2-methyl, but, 3-ine, 2-ol. For multiple C double bond C, C triple bond C, or OH groups, the number of carbons prefix ends with A, such as buta, penta, hexa. For C double bond C or C triple bond C compounds that are multiple, ane for multiple OH compounds. Use comma-separated numbers from the lowest number to the highest number for the position of the first carbon in each carbon-carbon double or triple bond, or the position of each OH. You also have to end the name with di, tri, tetra, etc., plus the ending for whether you have a carbon-carbon double bond, ene, carbon-carbon triple bond, ine, or an OH group, ol. For combination of multiple C double bond C, C triple bond C, or C triple bond C, and OH groups, you use the N, En, or ine, Yn component when the name ends with a vowel, such as ol. Use ene, or ine, when the name ends with a consonant, such as diol, triol, etc. So, N-ol, ine-ol, or en-diol, ine-diol. For C double bond C and C triple bond C mixed together, the name will always end with the number for the position of the carbon-carbon double bond, followed by En, and the number for the position of the carbon-carbon triple bond, followed by Yne, ine. The lowest possible number will be given to C double bond C. You will use Ene, en, if it's in front of a consonant that's set in front of Yne. So, en, diine, en, triine, etc. Practice problem 6. Name each of the following compounds. In all of these cases, you're going to have multiples of the functional groups that we've just discussed, the carbon-carbon double bonds, carbon-carbon triple bonds, or the OH groups. And you may even have a mixture of the two in the structure. So make sure you follow those rules that you see in the previous slide. At this point, you'll want to pause the slide to work on the problems. Answers to practice problem 6. In part A, we have a 5-carbon chain with 2 carbon-carbon double bonds. So, we number the carbon-carbon double bonds with the lowest possible numbers, 1 and 3. There are also 3 bromines, 2 at position 1 and 1 at position 5, so that makes that tribromo. The carbon-carbon double bond between carbons 3 and 4 is cis, so the full name would be cis 1,1,5-tribromo penta 1,3-diene. In part B, we have an 8-carbon chain. There are only carbon-carbon triple bonds present at positions 2 and 6. So this is octa 2,6-diene. In part C, we have a 5-sided ring, a cyclopentane. There are 2 OH groups present at positions 1 and 2. There's also a tert-butyl group at position 1. The OH groups, the identical groups, are pointing in opposite directions. At position 1, it's pointing down. At position 2, it's pointing up. So that's trans. So the name for this would be trans 1-tert-butyl cyclopentane 1,2-diol. In part D, we have a 6-carbon chain. The OH group is numbered with the lowest possible number compared to the carbon-carbon double bonds. So we will number from left to right. So we have 1 for the OH group. The double bonds are at positions 2 and 3 and 5. There are 3 double bonds. That's a tri-N. So the name for this compound would be hexa 2,3,5-tri-N 1-ol. In part E, we have another ring. It's a 6-sided ring this time. It has both OH groups and carbon-carbon double bonds. The OH groups are pointing the same direction, so they are cis, as would be the hydrogens associated with them. And we would call this compound cis 3-methyl cyclohexa 3,5-diene 1,2-diol. Note that in numbering the OH groups, we number so that they get the lowest possible numbers, but we don't want to burn the carbon-carbon double bonds, give them really high numbers, so we number counterclockwise so that the first carbon-carbon double bond gets to have a number 3. But we also don't want to upset the apple cart for the methyl group. We don't want that to be number 6, so we give that number 3 as well. In part F, we have an 8-carbon chain. This is a mixture of carbon-carbon double and triple bonds. There are 2 carbon-carbon triple bonds, so that's a diene, and 2 carbon-carbon double bonds, so that's a diene. Remember that you give the lowest numbers to the carbon-carbon double bonds if possible. So this would be an octa, 1,5-diene, 3,7-diene.